All right, let's go ahead and get things kicked off for today. I want to welcome everybody to our session here today on enums, structs, and traits in the Rust programming language. These three topics or features of the language are really the essential building blocks of Rust programming. When you go to build applications and build more complex data structures, and then the methods and stuff that go along with them. These are really the essential building blocks. So I'm excited to be able to talk to you today about what these building blocks are, how we can use them, and explore some code with them. Before we get into the actual content of today's session, let's give a quick little overview about us. We're training for programmers. Our goal is to deliver human-centered AI-empowered computer programming training. Our goal is to deliver the same kind of content that you would see in a traditional big corporation corporate training course, but to deliver that same content through these free sessions that we do. Also, we set up these trainings so that anybody who has a web browser and an internet connection can not only participate in the session, but will be able to code along with us. And we'll talk a little bit about how to do that once we get to the actual content itself. We're focusing in on in-demand languages. Our language right now that we're doing a lot of sessions on happens to be Rust, but we also teach a lot of other programming languages as well. Our goal is to help empower people to work where they live. So instead of people having to get on airplanes and move to different parts of the world in order to get a programming job or to get programming training, our goal is to help empower people where they are so they can be with their families and their communities and enjoy, doing the programming work they love to do. And then, of course, we like using AI tools here to help enrich the programming experience as well as the learning experience. Here are some ways you can connect with us. Our website is trainingforprogrammers.com. We're also on LinkedIn. We have a YouTube channel where we post videos and things up there. And of course, here's our email address. Before we continue on, I'm going to put a couple of things here in the chat. Bear with me 1 second here. So we have a Discord group we're trying to grow. If you'd be interested in joining, you can check it out there. Any questions that we receive in today's session that I don't know the immediate answer to, I'll be answering those questions in the Discord server. And then here's a link to us on LinkedIn. We would love it if you would follow the company and stay up to speed on all the things that we put out there in terms of events and stuff like that. And then, of course, the YouTube channel. I will be posting the recording for today's session to the YouTube channel within 72 hours of this ending. So I'll send out the link too, but you'll be able to access it there. So our next upcoming training session is actually not going to be until July. I have a really busy June, and so trying to fit in a training session in June is probably not going to happen. But the one we're going to do in July is going to be a 6-hour one. It's going to be on Wednesday, July 3rd. It'll start at 9 a.m. Eastern Time, US, and will go until 3 p.m. Eastern Time. And we're going to take a look at building web apps with Rust and Leptos. This is the final slide, but I'm going to do it before we do the demos because I never have time for the final slide at the end. So first of all, thank you so much for registering and attending. Second, once we're done with our session today, take time to go back and review the demos. If you have questions, join us on Discord. You can ask questions about the demos. I'm more than happy to answer them on Discord. We would encourage you to make use of that resource. Within 72 hours following the event, I will send the recording, a link to the repo, and a badge to everyone who attended the live session today. So you'll get that within 72 hours. It'll probably be closer to the 72 hours than closer to, let's say, a few hours afterwards. I'm going to be traveling and stuff the next couple of days, and so it'll probably be a couple of days before I'm able to send all that out. Follow us on LinkedIn and Eventbrite to stay up to date on future events. And then we'll have a kind of an end of class survey I'll have you quickly fill out for me just to offer some feedback on the session, as well as offer potential ideas and stuff for future training sessions that we can do. Before we dive into the actual coding, just a quick little overview of what Rust is. Rust is a fast, memory-safe, concurrent systems programming language. It focuses in on speed, memory safety, and parallelism. It has a unique ownership model that allows us to avoid doing manual memory management, but also allows us to avoid a garbage collector. It's the actual ownership model is enforced by the compiler. It's actually one of the more difficult aspects of learning how to write Rust code. But once you understand how the ownership model works, it gets a lot easier to work with. And it's definitely a powerful way to have safe memory management without the overhead of a garbage collector. It provides a very powerful type safety and error handling features. In fact, we're going to be looking at some of those as part of our discussion on enums and structs and traits today. Supports zero-cost abstractions, allowing high-level features without performance penalties. And then Rust is used for a whole wide variety of applications, writing web servers, operating systems. I actually use it a lot of times to do task automation type stuff, believe it or not. Things that I might have used Python for in the past. Actually, I find Rust as a great alternative to use. It's a little bit trickier to use at first, but once you really understand it and start building things with it, it's really it's actually a really nice way to design and build software. All right, with that said, let's go ahead and get started doing some programming here in Rust. So I'm going to put a link here to our repository into the chat. Now, as we go through and do this, if you have any questions, feel free to put them in the Q&A. I mean, you can put them in the chat too, but it's actually a little better if you put it in the question and answer box. That way I'll know to answer them and I can check them off when I'm done. But if you could, go ahead and click on that GitHub link. It'll load up the public repo here. Now, if you'd like to code along with me for this, what I recommend you do is fork the repository. And then on the fork that you create, go ahead and create a code space. So fork the repository and then create a code space on the fork. All right. So once you've done that, you'll have something that kind of looks like this that will come to life, and you can do your programming here inside of your actual browser. So I have the whole thing set up to work for a Rust project. It'll install the various Rust extensions and other tools that you need. If your GitHub account happens to have a Copilot license, Copilot will also work with this. And what we're going to be doing is we're going to be navigating these various demonstration projects I've created to explore some of the different features that are in Rust. Down here at the bottom, there's a cargo toml file, which actually links all of these projects together in a workspace. This cargo toml file, putting it all in a workspace, is critical to tools like the Rust Analyzer to be able to provide all of the Rust language support. So if you decide to take this repository and go in and kind of explore it, modify it, make changes, whatever, just realize that this cargo toml file in the root folder with all the projects listed is essential to getting Rust Analyzer support within these individual projects that I've created. Okay, so with that said, let's go ahead and get started here. We're going to basically take a look at enums, structs, and then we're going to get into traits, okay? So as you know, an enum is basically a data type where you have some kind of list of or set of fixed values that the variable can contain. So for example, here we have enum direction. It's got 4 possible values. We have up, down, left, and right. And we can come down here to our code in the main function, and we can have a variable here of player direction, and it'll be of type direction. And then we can assign one of these values to that variable. So if I were to come in here and run this code, you'll see that it outputs here moving up because I assigned the up value to that player direction. If I came into here and said down, and I clicked on run, you'll now see it says moving down. If I tried to assign it some value that didn't make sense, let's say I had move cool, and I tried to run this code, you'll see I get a compile error because cool isn't one of the possible direction values. Now, enums are available in many programming languages. Enums are not something that is specific to Rust, okay? But Rust takes these enums and adds additional capability to them. If I come under the O2 enum with data folder here and open up main RS, I want you to take a look at what we can do with enums here in Rust. So I have an enum called IP address kind. It's got two values, v4 and v6. So an IP v4 address and IP v6 address. The v4 address is a tuple of 4 unsigned values. The v6 address here is a string value, okay? Now, what's cool about this is down here when I do the assignment of the v4 and the v6, I can specify these values as part of creating the value here for the loopback variable. Then, up here, when I call print IP address, I pass in my IP variable, which is of type IP address kind, and we use a match statement. And what we have the ability to do is with the match, we can reference the enum values, as you might expect, but we can actually capture the data here into these individual variables that are associated with the definition of the enum. And then over here, we can have code which makes use of those variables. In Rust, enums can have data, and that makes them super cool and super useful for a whole lot of things in Rust. I think one of the reasons why enums aren't better used in most other languages is because they don't have this kind of capability. So often with an enum, you need more than just up, down, or whatever. You need additional information that goes with whatever option is selected. Rust provides that capability here. So now if I were to come in and run this code, I get home and it prints out 127.0.0.1, which you can see here. And then I get this one here with my v6, and it prints out this based upon what you see here. Okay. So we can have data associated with our enum. Very, very powerful. We can also have enums that have a struct. So I like to think of the enum with data here as kind of like a tuple, right? But as you know, a tuple is a bunch of data that's related to each other in one way or another. Not the same data type, but related to each other. And is typically accessed through some type of index or something like that. It's positional in nature. When you work with a struct, you're working with something that's more like a key value pair. And we can actually take the concept of a struct, which we'll talk about in more detail later, and combine that with the enum. So here I've got a shape circle and a shape rectangle. And then on that shape, I can have, or circle, I can have a center and a radius, and then I can have a top left and a bottom right. So this is the data that's associated with the particular value there of the enum. Now, why is this ability to have enums with values so important? As you know, in Rust, we have this very aggressive static memory analysis mechanism, right? So when a Rust program compiles, it really wants to know the size of data types at compile time. Yes, it is possible to work with data types like box that will put, information out onto the heap, and there are many times when you will do that. But ideally, Rust really wants to know the size of things at compile time. By using an enum here, it can know the size of the enum at compile time, and yet we can hold different kinds of data in the enum. Typically, if you were going to hold different kinds of data that you didn't know about until runtime, you would have to store something on the heap. But with the power of enums and the ability for enums to hold data and for each option to hold a different kind of data, that gives the compiler its known memory size because it has to accommodate the whole enum. But it also gives us the ability to have different kinds of data depending upon whatever the value of that enum is. Enums with data values is really one of the keys to why, or to how Rust works the way that it does in terms of the borrow checker and all of the static memory analysis it does at compile time. Anyways, if we come into here, we'll do the rectangle first. So we're going to have a shape rectangle. We're going to use that match statement again. And this time, if we match the circle of the rectangle, we'll pull off the appropriate data and write some code to use it. So I'll come into here and I'll go ahead and run this. And you can see rectangle with a top left at 0, 5, and then a bottom right of 5, 0. If I come up to here and do the circle, and we run this, circle with the center at 0, 0, and radius 5. Now, like I said, in other languages, if I had things that actually had a different data structure, I probably would have to push that off to the heap, right? So you would see some type of memory allocation, or if you're using a garbage collected language like Python, you would just see a new object being created. But here in Rust, all of this is all going to be on the stack, and its size is going to be known at compile time, which is a more memory safe way of doing things. Remember, whenever you allocate things onto the heap, there's always the possibility that the allocation is going to fail. With this, the memory is allocated as part of compiling the program. So there's no allocation or additional allocation at runtime. All right. Let's take a look here at a very common option, or a very common enum, I'm sorry. And it's called the option enum. One of the big problems that a lot of programming languages have are null references. And this is a problem that you have not just in, let's say, manually managed memory languages like C and C++, but you also have the same problem in languages like Java, C#, Python, JavaScript, where you can have these null references floating around. Some languages like C# and TypeScript have become particularly aggressive about making sure that you are checking for null references. But historically in programming languages, null reference checking is something that a lot of programmers forget to do. And they're also the source of a lot of runtime bugs and failures. So the way that Rust handles this is Rust doesn't have null references. Instead, what Rust does is it provides an enum called the option enum. The option enum can have a value of what's called sum or it can have a value of none. And you actually are forced to handle this value of none when you go to work with the option, right? If you come into here and you don't handle the none here, you're going to get a compilation saying none not covered. So it forces you to handle the none, which is a situation that would typically be that null reference in another language. But in this case, the none is an actual value, but it forces you to handle it when you're working with things like the match statement, which then, of course, results in safer code because now you have to think about the situation where you don't get any data back. So in this case, we have a vector of numbers, and we're going to use the find number function to look for a number within the vector. Now, the vector is a fixed vector of numbers, so 30 will be found, but 100 will not be. So this function literally does nothing more than simply just iterate over the vector that's supplied and then return back the index. You'll notice if it finds the index value, it returns sum with index being passed in. Remember, our enums can have data. So the sum value of the option enum actually has the value that was found. If we have a none, there's no value to pass in because, well, nothing was found. So if we run this code, let's see what the output looks like. So found number at index 2, and then we have number not found in list. Pretty cool, right? So there's our setup there. Now, let's take a look at using the option as part of a struct. So in the last example, we simply just had the return value of a function be an option. But where you'll see option being used a lot, especially if you're working with things like REST APIs, is where you call the REST API and the JSON may or may not contain a value for some particular property being returned. To deal with that, we can use the option on an individual struct property, and then we can handle that situation where, in this case, middle name may not have a value. So down here, when we go to create user 1 or user 2, you'll see that we use that sum and set up the middle name like that. Down here, you'll see for middle name, we set it to none. And then we have a print username, and that method down here receives that user via reference, and we match the middle name. So if we have a middle name, we'll print out the name here. If we don't have a middle name, then we print it out like this. So you can see a none doesn't necessarily mean like an error or something went wrong. It just means that we have a different way of working with the data that we do have that might be a little different than if we actually had a value in this case for that middle name. As we're going through here and doing this, don't hesitate to ask questions in the Q&A. Be more than happy to answer those, as we go along. All right, let's take a look at our last little enum, strictly enum example, and then we'll move into talking about structs. So the result enum is used to do error handling. Most of us in languages like C++, Java, C#, whatever, we're familiar with the whole concept of try and catch blocks, right? Python and JavaScript do the same. So we try a piece of code. If it fails, an exception is thrown, and then we catch it. Well, that exception that's thrown is a special kind of it's a special kind of object that you're working with. It's not just a regular object. It's an object that has things like a stack trace and has some unique qualities about how it's caught and rethrown and things like that make it different from the rest of the code that you're working with. In Rust, we don't throw exceptions. Instead, we treat the error as we would any other value. So instead of the error or the exception being something that is extraordinary, we treat it as just one of the possible results of, in this case, of the function that we're calling. So in this case, we have this read file contents. The return value is hopefully going to be a string, but we're going to wrap it in the result enum so that it could be a string or it could be an IO error. Once again, the benefit to using the enum here is I have a fixed memory size for whether it is a string that comes back or an error that comes back. Now, of course, a string is a little bit different from other data types. It itself is kind of dynamically allocated. But in terms of knowing that we're going to have this pointer to a string, we have that covered here in the size of the result. So we come into here, we open up the file, we read the contents, we read it into the string, and then we return it. Now you'll notice here I have question marks. These question marks basically will automatically return the error from this code as the output of this function. So I don't have to write code that says, oh, did an error occur, now return. I put the question mark, and then if an error occurs, the error is returned immediately and the function is exited. So if I have an error here reading the file open or reading the file name here with file open, it's going to output an IO error. If I have a problem here reading the contents of the file into my contents variable, then I'm going to have an error. So the question mark is a shorthand way of returning that error back. Down here, when I call match read file contents, I'm now forced to handle the OK and the error. So if everything worked out okay, I can get the contents and process it. If something goes wrong, I get the error, and then I can print it out. You can see this is very different from most of the other traditional, conventional programming languages that people have used for decades. The way that we're using these enums that have values, the way that we're using the match statement to force us to consider all the possible outcome values, so on and so forth. So if I run this, let's see here. We got an error reading file. Let me actually go to the terminal here and go to 06 and say cargo run. That way it finds the right file. There's the example text, but I have to run it from that folder. Otherwise, it doesn't find the file based upon the working directory. Okay, so now that we have that, let's go ahead and turn our attention to structs. So the first building block are enums. The second building block are structs. Now, a struct in Rust is similar to a struct in, let's say, the C programming language, similar to like a record in Pascal. You could kind of think of it a little bit like a class from like C++ and Java and C#. You could definitely think of a struct as like an object literal in JavaScript, or just an object in general in JavaScript. You could also think of it as like a kind of like a class in Python too. The big difference between a struct and a class is a struct is really just a data structure. It doesn't have any methods implemented on it. Whereas in a language, let's say like C#, Java, and C++, the actual classes have methods implemented on them. So a class is a combination of the data and the methods. Now, in this case here, we have a struct person. Person has two fields, name and age. We can make them be whatever data type we want them to be. And then down here in our program, we're going to create a person. You'll notice there's no new operator built into Rust. In fact, Rust has no concept of constructors. If you just want to create a struct, you simply put the name of the struct, the curly braces, assign the data values, and you create a struct. Remember that this is all being done on the stack. We don't have any code here that's putting anything out onto the heap or something like that. So when we go to create this variable, this is going to be a known size. And then, of course, we can utilize the struct by simply saying person.name, person.age, and then here print it out to the screen. Okay. There's another kind of struct called a tuple struct. Looks very similar to the enums with data. So here I'm going to have a struct color with an I32, I32, I32 RGB. And when I want to create one, instead of using curly braces to create it, I'm going to use parentheses, and I'll have my 3 values in positional order. So for example, here we have black. And then if I want to print out each member of the tuple struct, I use its positional location. So black.0, black.1, black.2. Okay. This syntax here always kind of looks a little weird to me. I'm used to using things like square brackets that you would see in other languages. But in Rust, essentially what we're doing is treating the positional index as like a property. But instead of it being a named property, the property is that positional index. All right. Struct methods. So we have our struct rectangle here with width and height. And then we have a impl block. So it is possible to connect methods to a struct, but it's not in the same way that you would work with classes. Okay. We're not really creating a class here. What we're doing is defining some methods that will be accessible off of the struct once we create it. So here we have an area method and a can hold method. If you look at that ampersand self, this is actually going to make this method available to us on the actual rectangle that we're going to create here. You will see in the next demo that we can add methods here that don't have an ampersand self. Those methods are then accessed using the double colon syntax that we'll talk about in a moment. But on your rectangle instance, you can access these methods, and of course, self will then be whatever instance you're working with. So in this case here, for rectangle 1, self.width would be 30, self.height would be 50. For rectangle 2, self.width would be 10, self.height would be 40. And so we're going to create 3 rectangles on the stack. And then down here, we'll call those methods on those rectangles. All right. Let's take a look at associated functions. So you'll notice in this one, it's a little bit different. There is no @self on the new function. The new function is not to be thought of as like a built-in language feature like you might find for constructors in other languages or what have you. The new function is just a name that we've chosen. It's a pretty common choice of a name to create a new rectangle and have some logic and stuff used to help create it. So it's a pretty common name to use, but you don't have to use the name new. It's just a function like any other function. You'll notice there's no @self, so it's used before you have actually created the rectangle. This is called an associated function. So down here, when I say rectangle, I refer to the struct type, not the rect instance I'm creating. And I followed up with double colon, and then I can call the associated function, in this case, new. Pass in my 30 and my 50. And then down here on the actual rect instance, we'll get the value there of the area. So if I were to run this code, you'll see the rectangle is 1,500 square pixels. Okay. One of the big things that we have to deal with in Rust are mutations, right? So as you know, when you create a variable in Rust, by default, that variable is immutable. If you want to mutate that variable, then you have to declare that variable with the mute keyword, MUT. But you also then have to deal with mutable references versus immutable references, and it gets really complicated. This is where we get into all the borrow checker stuff and everything else. Well, that also translates over into working with methods here on these structs. In this example that we had here first, a second ago, you'll notice that area and can hold did not actually modify any of the fields on the struct. That's why we just have an immutable reference, ampersand self. We're not modifying any of the fields on the struct. Over here, we are going to modify the fields on the struct. In order to do that, we have to get a mutable reference on self. This concept of getting the mutable reference on self is the key to how Rust knows we are mutating a struct when calling a method on it. If you think about it, just calling a method on a struct instance, how would you know that that method was going to mutate the underlying struct? In any other programming language that has a similar memory and function mechanism, there's no way to know. But in Rust, because of the ampersand mute, we can instantly look at this and know that this method is going to mutate the counter struct. And because we know that, if we try to use counter down here without the mute keyword, then we're going to get the red squigglies, right? So think about, how would Rust know that we're actually mutating this? Well, it knows it because as part of the method definition, we have to get a mutable reference to the underlying struct. You don't get that automatically. Over here, when we did the let rectangle, we didn't set up a mutable reference. So we could pass this in and read it, but if I had come into here and done self.width is equal to 1, I get a cannot assign behind an immutable reference. I'm going to need a mute reference to do that. So anyways, that's how Rust is able to know whether or not calling a function is going to modify this variable. And that's part of how the whole borrow checker mechanism works. It's actually really cool. I remember when I was first working with Rust, I would look at code like this and I would be like, how does Rust know I'm going to modify counter? Right? And it was because of the ampersand mute up here. Now, typically when you run into this issue, it's not with your own custom struct and your own custom impl block. It's using something like a vector. And then you call one of the methods on the vector to mutate it. And then it complains saying you don't have a mutable reference. And you're like, well, how do you know that function's going to mutate it? Well, it knows because of the way these functions are defined. Okay, so if we were to come into here and run this code, 5, 6, after reset will be down to 0. Okay. All right. Now, we have ourselves a bank account. We have our balance. And then we have some methods on the bank account. This is just a little bit more involved example. So I have a new method where I'm going to create that bank account and return it back. I have my deposit and my withdrawal method. You'll see here we're going to bring in the result type. So if you try to take out more money than what you have, you get an actual error. So you can see that kind of coming together there. And then down here, I have a method that just needs an immutable reference so we can get the bank account balance. So if I come down to here now, I'll create the bank account. I'll print the balance. I'll do a deposit. I'll print the balance again. Then I'm going to try to do a withdrawal. So we'll bring in the match statement. We'll attempt to do the withdrawal. If it's successful, we'll output the success message. If not, we'll print the error. So if we run this code, there you go. Initial balance 1,000, after deposit, after withdrawal. And if we try to do another withdrawal of 1,500, we have insufficient funds. So you can kind of see the result enum, the mutable references, the immutable references, the impl block combined with the associated function for creating the new bank account. You kind of see all that kind of coming together here. All right. Let's talk a little bit about nested structs. Can you have structs that have fields that point to other structs? Of course, the answer to that is yes, you can. So you'll see here we have a struct address with a street, city, and zip code. We then have this impl block that has a full address function on it. You'll notice it's a method of the struct because we have the ampersand self. And then it returns back a formatted string that has the street, city, and zip code. We then have a struct person with a name and an age, as well as the address. And then on the person, we're going to create the person with their name, their age, street, city, zip code, and then you see it being set up just like that. And then down here, we can reference address in any of its members, functions, or data fields, whatever, just like you would in any other language with the whole dot syntax approach. So if we come into here and we run this, hi, my name is Alice. I'm 30 years old. I live at 123 Main Street, Springfield, 12345. And that's all created from here. One thing I want to point out is you'll notice we're using string types here. We're not using string slices. As you know, in Rust, there's always a little bit of confusion about what's the difference between string and string, okay? This string here is a string slice. Basically, you have a memory reference to a string that's owned by something else. The problem with using the @ string or the ampersand string here is you have to get into lifetimes. You have to ensure that other string will be alive for as long as you're going to have this reference to a slice of it. You don't want to do that when building structs. It starts to make things really complicated. You'll notice when people build structs, they always give each field its own string of the string type, okay? So you can go learn more about the string slices versus strings, but that can throw people off sometimes. Okay. Before we go into our final section here on traits and look at some pretty cool stuff that you can do here with Rust, what I wanted to do is drop into the chat real quick. You don't have to fill this out yet, but I do have a little bit of a feedback form that I'd like you to fill out before you take off today. So in the chat there is a link to the feedback form. It's hosted on JotForm. If you click the link, you can fill that out. You don't have to fill it out at the moment, but I wanted to drop the link in there before we get to the end, and then everybody drops off. So if you get a chance before you go, I would appreciate any feedback you'd like to offer on the session. All right, so I think we have a good idea of what enums and structs are. What about traits? Traits are this third building block. Traits are something that that make Rust unique compared to most other languages. Some languages are actually starting to have traits now, but it is definitely something that makes it unique when compared to C++, Java, C#, so on and so forth. So as you know, in a language, let's say like Java, you can program a class according to an interface. That interface will have basically a contract which describes the various methods the class must implement. And then the class implements those methods, but then that class can be used anywhere that interface is accepted. Traits are kind of like interfaces, a little bit different, more powerful in many ways, but they're kind of like interfaces. So what we're going to do is we're going to take the struct person, and I want to be able to use struct person as part of doing my formatting of strings. So if I want to say print line, curly braces, and then person, in order for this person to fill these curly braces, it needs to implement the display trait. So this format : display is called a trait, and structs that implement this trait will have this method called when formatting is needed. So this will actually have the effect of calling the format method up here. If I don't have this block of code, now I get person doesn't implement that trait, okay? If I come into here and do something like this to do like a debug print, I still get that because it doesn't implement the debug trait. So if you ever see where people have code where it looks like this, and they're deriving from debug, what they're really doing is using a macro to implement the debug trait for this struct. Now you can pass it into here and print it out. But let's say I don't want to debug. I just want to print person. Well, in that case, the debug is not enough. I need to actually implement the display trait and then implement the format method, which will then take the data, which we have through the immutable self-reference, and produce a string for us. So we come into here, we use write, and then we have our formatter, and then we have our string. And then, of course, each of these properties, depending upon their data type, also have to implement the display trait as well. So now I can come down here and pass this in, and it will work. So you can see it's kind of like an interface, right? Because I had to have this contract available so that the print line could actually call format. But it also provides an implementation for me to use. Now, it's possible for traits to have a default implementation, and then you just simply apply it like we're doing here. It's also possible that you can override that default implementation with your own custom implementation. Now, let's take a look at this example here. So I have this trait called drawable with the draw method defined but not implemented. So there's no default implementation. I have struct circle and square. You'll notice struct circle and square don't contain any fields on them. It is possible to create a struct with no fields, just so you have something that you can call these methods off of. So for example, here, I'm going to have my struct circle, and I'm going to implement drawable for circle, and there's my draw method. You'll notice it doesn't make use of any data fields or anything like that. It just says drawing a circle. I'm going to implement drawable for square. Same thing as here. Now, if I come down to here, you'll see I have a circle and I have a square. They both implement draw. They both implement the drawable trait, but circle and square are two different things. Well, in a language, let's say, like Java, you would come into here and say your shape will be of type drawable. And then you might think, well, I'll just come into here and say draw shape circle and draw shape square. So this would be a very common piece of code that a person new to Rust but had experience in C# or Java, they would try to write code like this. They would look at this and say, okay, yeah, I get it. This drawable is like an interface, right? It's a trait, but it's like an interface. I'm going to go ahead and implement the interface for circle and square for drawable. And then down here, I'll have a method with the drawable type, and then I'll pass it in, and everything's going to be perfect. This is where we start to reveal a lot of stuff in other programming languages that we take for granted, a lot of memory things we don't really think about when we're writing our code. Yes, the shape that I receive here needs to implement drawable, but I can have any number of different structs of different shapes and sizes implement drawable. How does Rust know at compile time what the size of a trait is? It doesn't, because a trait doesn't really have a size until it's connected to a struct. But I don't know what struct I'm passing in until runtime. I've got a problem. You see, when we work with our traditional variable declarations, we are working on the stack. The stack must know the size of memory at compile time. But we have situations where we don't know the size until runtime. Well, what do? We push it out to the heap. Okay, that's fine. We'll push it out to the heap, which is exactly what Box was doing. Box was pushing the data out to the heap. Our problem, though, is how do we take this box and connect it to drawable? Well, we could bring in box like this, okay? But here's our problem. We don't know which of these methods we're going to be calling. We don't know the memory structure of circle or square. Essentially, what we're going to have to do is something called dynamic dispatch. We're going to have to resolve at runtime how to call that draw function. So the way we're going to do that is we're going to put the dyn keyword in here. Now, what's the downside to what we just did here? The downside is now I've moved from the stack to the heap. That's what the box did. So now I've got heap allocated memory. Now remember, Rust is going to clean all this up as part of its compilation and knowing the memory lifetimes of things and creating things and deleting them. So the fact that it's going to have to be cleaned up itself isn't really a problem. It's just, it's the nature of working with the heap. But our problem is going to be that we're not going to be able to resolve that draw method until we get to runtime, which means that the code will run a little bit slower. You could have potentially other issues. So when we work with traits, it's great that we can implement them on these different struct types. But keep in mind that if we start trying to program things the way we think of interfaces, we, in essence, start having to slip back into things like dynamic dispatch and things like that and resolving stuff at runtime. There's a reason why things like C# and Java work the way that they do, the way the garbage collection works, the reason why things have to be allocated dynamically at runtime because of language features like an interface. Whereas in Rust, we really are trying to know the size of things at compile time and do as much as we can on the stack. Okay. Let's take a look at a common usage of this box dine pattern, and it has to do with error handling. Now, I used to write my Rust code like this all the time, where essentially what would happen is I would need the result enum. A successful operation would return some type of data, but I had the possibility of an error. But here's the problem. I have different kinds of errors that can result. This error here is a standard IO error. This error here is a standard IO error. This error here is a standard num parsent error. So if I try to take this and put this into here like this, that's not going to work for this one. If I try to put this into here like this, that's not going to work for these two. Well, if I don't know the size of something, I guess I can push it to the heap. But then what am I pushing to the heap? Well, what I'm going to push to the heap is the error trait with the box dine error. So this works. There's nothing wrong with this Rust code. You'll see lots of people follow this pattern all the time. And in fact, if you come from a C# or Java background, this feels like a very natural way to solve this problem. But what's the issue? I'm having to bring in the heap and dynamic dispatch to resolve what type of error I'm working with. And that's the downside to it, is that I'm having to push things off to runtime because I have different kinds of errors that could come back. If we run the code, well, actually, let me run it. You'll see no such file or directory. And if I actually go to the folder here, which will be the folder 16, and I say cargo run, you'll see now I get back number is 42. So everything works, it all compiles. But whenever I see code like this, it kind of reminds me of the way that I used to do error handling in Rust. And I would think, this is a perfectly good way of doing it. There's other ways we can restructure this to eliminate the dynamic dispatch and to eliminate the heap allocation. Let's take a look at one of those approaches. Now, this gets to be a lot more coding, unfortunately. But the benefit to what's going to happen here is that I'm going to know the size of my error at compile time, and I avoid dynamic dispatch, and I avoid allocating heap memory in order to handle different kinds of errors. So I'm going to start off first by creating my own custom error enum. Remember how we can have these different values for the enum, and these values can have data. So the IO will have the IO error, parse will have the parse int error. In order to create a custom error, you have to implement the display trait on the error enum. So just like I can do an implementation for a struct, I can also apply traits to enums as well. So you can see here inside the format, I use my match, and then I use my matching here to then write the appropriate error information if you wanted to print it out to a string or something like that. Here, I've got the from trait that knows how to receive an IO error and basically produce a custom error IO, and how to take a parse int error and produce a custom error parse error. Pretty cool, right? So the display trait outputs a nice string. The from trait allows me to convert from the original error into the custom error that we're working with. Now, if I come down to here, now when I have my result I32, I say result I32 custom error. No boxing, no dynamic dispatch. Here, I have the same question marks that'll return the custom error IO, custom error IO, custom error parse. But because of the from trait, when this value is returned, Rust will automatically apply the correct from function to take the original error you see here and transform it into the custom error being returned back. So what have I accomplished? I now know the size of my error type at compile time. I don't need to do boxing out to the heap, and I don't need to do dynamic dispatch. Was there more code involved? Yes. But I have a better, more memory safe program. Remember, it's not that the heap is bad or you'll never use the heap. You will use the heap all the time. But if it's possible to keep something on the stack because that memory size is known at compile time, that is a safer way to code. In fact, there's people who, when they write their C programming code, depending upon what they're writing it for, they don't even allocate memory on the heap. They write their C code in such a way that everything is stack-based. That's tough to do. But for Rust, it makes it a lot easier for us to do that. Okay, now let's talk about the magic here of how this from trait takes the IO error or the parse error and converts it to the custom error. So what I did was I have a person here and I have a from trait being implemented. And basically you can take a tuple of two values and create a person. If we take a look at our code here, I'm going to take this tuple that I'm creating and assign it to person tuple. I'm going to call person from explicitly, like you see here, and it's going to return back a person and print that person's information out. This is pretty straightforward, right? I'm simply just calling the from method, passing in the tuple, no big deal. Another way that I could have written this, though, is I could have created my person tuple and called the in2 method on it. The in2 will basically call the from to produce the appropriate type that you see over here. So for example, if I got rid of :person there, all of this code would still be fine because it knows it's going to be a person. But what if I got rid of :person here? Now you see where I get another person has a red squiggly? The reason I have a red squiggly is because the in2 needs to know the destination type to know how to do this conversion. So if I know the destination type here, the in2 is smart enough to pick the right from function. Pretty cool, right? So that's what's happening over here when I output these errors. I don't have to explicitly convert them to custom errors. Instead, the question mark is going to handle that in2 call, and then the from here will convert that error for me. Okay? Will convert that error for me. All right. Let's take a look at a custom trait. All the traits we've looked at so far were ones that are just built into Rust. But you can actually make your own custom traits as well. So if you take a look here, I've got a trait summary that has a method called summarize, and it has a default implementation. So here I have an article and I have a tweet. For the article, I implement the summary trait, and it's basically going to provide that custom summarize method and then utilize the data of the struct to return back some type of formatted string. No big deal. For the tweet, though, you'll notice I'm just going to say implement summary for tweet. I'm not going to provide a method definition. Instead, it will use the default here. You could kind of think of this a little bit as like overriding an inheritance in a traditional classical object-oriented language a little bit. You could kind of think of it like that. So down here, I create my article. I create the tweet. And then down here, I print out the summary of my article and I print out the summary of the tweet because they both have that summarize trait applied to them. Okay. Let's take a look at our last example here. So before we go into the last example, thank you all for attending this, and don't hesitate to reach out to us on LinkedIn or on YouTube. And then, of course, if you could fill out that form before you take off. We're going to be changing up the structure of our sessions here starting in July. Instead of using Zoom, we're going to be switching over to Microsoft Teams. And instead of registering on Eventbrite, we're going to be registering through the Teams meeting itself. So we're going to switch some of our processes up here a little bit. So if you're interested in participating in the Rust Leptos upcoming session or any other future session, just be aware that the sign-up process is going to be a little bit different moving forward. With that said, let's go ahead and talk about our last little demo, and then we'll call it quits for today. So it's the same summary and article and tweet that you saw before. But what we're going to do this time is we're actually going to create an independent method here called print summary. It's going to be a generic. You'll notice, though, that the generic is going to require you to pass in a struct that implements the summary trait. By using a generic here, instead of, remember over here we had the dynamic dispatch, right? Where we had to resolve this at runtime. By using the generic here, the generic trait, this is how we achieve that zero cost abstraction that we talked about in the overall summary of Rust. So this right here is not a zero cost abstraction. Yes, we are abstracting the fact that we can pass in something that implements the drawable trait, but we're having to resolve things at runtime. When we talk about a zero cost abstraction, we're talking about not having to resolve things like dynamic dispatch at runtime. Those things like dynamic dispatch, they add overhead to the execution of our code. Well, the nice thing about generics in Rust is that with generics in Rust, it's actually going to create a version of this method for each type that actually calls it. So we'll end up with a print summary for an article and a print summary for a tweet. It does make the compiled application larger because you have that method twice, but you get the zero cost abstraction at runtime, which is really our bigger concern. So by using the generic and then putting this constraint on it that it has to implement the summary trait, we're in essence using the trait as kind of the gatekeeper to call this function. And then at compile time, we create a version of this function for each kind of struct that calls it. And we're able to reuse that function in our code for any struct that implements the summary trait. So this is an example of utilizing generics to once again get us back to a fixed memory size, avoid the box, and avoid the dynamic dispatch. So this is another strategy that you can make use of. So in fact, let me kind of summarize those two strategies real quick. The one situation where I wanted to get rid of the dynamic dispatch was in this error handling. And the way that we ultimately did that was we created our own custom error enum. And with our own custom error enum, we had to implement some additional logic, but we were able to escape the boxing and the dynamic dispatch and get that zero cost abstraction. In the case of the last example, the way that we were able to escape the boxing and the dynamic dispatch was to leverage generics with trait constraints and then allow the program to be a little larger, but we get back to the zero cost abstractions. So as you can see, a number of different ways to solve these kinds of problems. And if you notice, they ultimately all go back to what? Memory management. If you really think about it, right? The idea of an enum having values is so we can have a known size for the enum at compile time, but we can support different kinds of data depending upon which enum option is the one that matches. We have things like the that custom error enum we created in implementing traits so that we could take other kinds of errors and map them into this enum so we have that fixed size in memory at compile time. And then, of course, the example of the generics. So, like I said, once you really start to grasp how this memory safe approach that Rust takes, once you start to grasp how that works, you start to see how it pops up in all of these different coding examples that we've done here today, but also in the last session we did with concurrency. You saw how we use the special arc type in order to share data between different threads and things like that. So yeah, the memory safe stuff really factors into everything, not just talking about declaring a variable, but how we work with things like traits and generics, and how we write our code with these basic building blocks of enums, structs, and traits. With that said, I want to thank you all for attending our session today. If we have any questions, I'll wait here for a second in case anybody would like to ask one. If not, thank you for attending. I will get the recording and everything sent out and uploaded as quickly as I can. And that's pretty much it. So thank you for being here today.